Hello, this is Teacher Nichols, and this lecture is on the velocity equation. The essential question today is how can I create an equation that will allow me to calculate the average velocity of a moving object? So this is the first big physics equation that we're going to be learning. This is also an equation that you may have learned in a previous science class, although we're going to add some things that are really important to be able to take this equation and do sort of next level work with it. So please do give it a listen and some attention, even if you think you know what's going on here. Before we get into the velocity equation, I want to revisit some of the variables that we'll be using for this entire unit on motion. The first is distance. We will use a d or a delta d to represent distance. And remember that distance is either where something is, that would be the d, or how far it moves, that's the delta d, the change in distance of an object. The units that we'll use for distance are meters. And it's important that you guys have a sense of roughly how long a meter is. A guitar is another meter-lengthed object if you've got one of those at home, or you can think about it as the width of a refrigerator. The second variable that we use to describe motion is time, which is either a t for the symbol or a delta t, depending on whether we're talking about when something happens or how long it takes. It's almost always how long something takes, not what time is on the clock. So delta t is used a lot more than t. The units for t in physics are seconds, and you should also have a little bit of a sense of how long a second is. There is like an official scientific definition of a second, and it's the duration of a whole bunch of vibrational periods of a molecule. You don't need to know that. Just say 1 Mississippi, and that will get you close enough to seconds if you don't have a stopwatch nearby. The third variable that we're going to be using in this unit is velocity. We will use a lowercase v to represent velocity, although we will sometimes have subscripts and operators that go along with that v, so make sure you know what those mean. And v in general is how fast something is moving and perhaps what direction it's moving in. The units that we use to measure velocity are the meters every second. Sometimes that's written m/s or pronounced meters per second, but I really like it an m over an s, and meters every second is how you will hear me say it in class. So how fast are things in meters every second? If you think about how many of these could you walk in 1 second, give or take 1, right? 1, 2, give or take. That's kind of the answers that would be a reasonable velocity for a human that's walking. In general, if you know miles per hour, like for a car, meters per second are about half as much. So a car going at 60 on the highway is going about 30 meters every second, if that's a helpful conversion for you to make. The third variable is acceleration, which is a. This is actually one of the trickier concepts in physics to understand, because so many people have been using it wrong their whole lives. People think acceleration and velocity are the same thing, when actually they're not related, really. An object can have a lot of velocity and no acceleration, or a lot of acceleration and very small velocity. So in any case, we will be working with that variable a lot to really help us understand it. But I did want to introduce it. The definition of velocity for physics is how quickly an object's velocity is changing. So it has to do with objects that are speeding up or slowing down. It doesn't just say how fast they're going, it's what's happening to their speed over time. The units of acceleration are the meter per second every second. Another way to write that is m over s squared. And again, we'll deal with that a lot more later on. All right, so let's figure out our first equation. This is going to be called the average velocity equation, and it's really useful to calculate the average velocity of any object in the world that is moving. So whenever we're trying to create an equation, we like to start by making that our dependent variable. So the question is, what does average velocity depend on? If there were things that you could measure to let you figure out the velocity, what 2 things would you have to measure to be able to calculate or predict an object's average velocity? In other words, what are the 2 independent variables that affect velocity? And if you think about it, if I ask most people to find the velocity of something, they just naturally know what to do. You got to measure the distance something travels, or delta d, and you measure the amount of time that it took. And the combination of those 2 variables is going to give us all the information that we need about average velocity. So the next thing you're going to do as you're attempting to create this new equation is for each of those pairs of variables, we need to identify what are the relationships between them. Are they linear, inverse? Hopefully not no relationship, or we wouldn't be using them, but are they linear or inverse? So if you're in class, we do this actual experiment, but if you're just watching this at home, do a little thought experiment. That means think about what's going to happen. So the question is, what is the relationship between delta D and the average velocity of an object, assuming that third variable is not changing? So in other words, if I have a really fast car and a really slow bicycle, right? If they both travel for 1 minute, what will we see, right? We know the car has a higher average velocity than the bicycle, so let's see what we're going to see. So here they are, car and bicycle. There's the car, there's the bicycle. Now stop. Okay, they've moved for the same amount of time. You should see that the distance the car travels is bigger than the distance the bike travels because the car has a bigger velocity. So the more the velocity, the more the distance. Hopefully that feels to you like there is a linear relationship between delta D and V average. Let's do another experiment. This time, I want to know what is the relationship between delta T and V average. So this time I got to keep the distance constant. That means I got my car and my bicycle, and they're both going to cover the whole distance of the screen. But I want to know, are they going to take the same amount of time to do it or not? Okay, so on your marks, get set, go. Okay, so obviously, if you had a stopwatch, the amount of time the car would take would be very small, and the amount of time the bike took was much bigger because it was moving slower. In other words, the higher the velocity, the less time it took to cover the distance of that screen. Hopefully when you see that, you think inverse relationship. And in fact, there is an inverse relationship between delta T and V average. All right, so we've got our two relationships between our variables. Now we get to do the magic of creating an equation. Please remember that when you're making an equation, you put the dependent variable by itself on one side, draw your equal sign, draw your line down the middle, and then we put all our linear relationships on the top. In this case, we found a linear relationship between V average and delta D, and we put our inverse relationships on the bottom. We had an inverse relationship between delta T and V average, so that goes on the bottom. And we're done. We've got the V average equation. This is the first big equation. V average is equal to delta D over delta T. A quick note, if you did learn this in an earlier science class, you probably just learned S or speed or V equals D over T without the deltas and without the average. But in this class, those operators are a really big deal because if you try to plug in initial velocity to this equation, it's not the same as average velocity. You're going to get the wrong answer. If you try to plug in, delta V, you're going to get the wrong answer as well. So you've got to be really careful to make sure that you are plugging in the right values, including the operator. Why do we have these operators? Well, the V average reflects the fact that most objects don't actually go at the same velocity for the entire interval that they are traveling. If you think of a car driving to Eugene or something, you might average 60 miles an hour over the course of your trip, but you're not going to be going exactly 60 the entire time, sometimes a little faster, sometimes a little bit slower. So this equation takes into account all those things and will just tell you what the average velocity is, not necessarily the velocity at each moment in time. As far as the deltas go, they're really important because velocity fundamentally involves an object moving, right? You have zero velocity if the object's moving. So maybe the object's located at the 50-yard line of a football field. That would be the D. But if it's just standing there, then we know it has no velocity. If you plug in a 50 for D, you're going to get the wrong answer, right? But an object staying at 50 yards, if you measure delta V, which is how much its velocity or its distance changed by, delta D, if it starts at 50 and ends at 50, delta D is 0. That's what gives us the appropriate velocity value that we're looking for. So delta D is how much distance is covered, not just the location. And the same thing is going to hold for delta T. Okay, We have reached the end of this video. As I usually do, I'm going to ask you to revisit the essential question, which is how can I create an equation that will allow me to calculate the average velocity of a moving object? What are the relationships that go into this? What is the importance of the math operators? So maybe you can think about those as you answer your essential question. And I'm leaving you with one comic. This is one of my favorite Calvin and Hobbes of all times, so hopefully you enjoy it as well. Thanks for watching.